All right, like I said, exam 2 is Thursday. I need to lock the doors. I made a mistake on the addition worksheet. You should look at the key. You should look at my comments. I didn't take any points off, but I saw arrows going the wrong way. I'm going to do an example here in a minute and talk about it. There were some acid-base problems. There's some stereochemistry problems. We'll get into that. So on exam 2, on Thursday, I'll probably won't be today, but tomorrow I'll get a sheet out for like who is supposed to be where. So 30 of you will be in this room. The rest of you will be upstairs in the labs. And I'll try to shake it up from last time so that this, if you don't like the lab, those of you with any kind of accommodations, you'll get a separate email to cover that. So I'll be in this room tonight, 6:30 to 8. First come, first serve. I'll ask people to wait outside. I'll ask some people to leave if you got here early. It's questions only though, okay? So if I come at 6:30 and even if the room fills up, but you all just sit there and say you don't have questions, I go home, all right? What else? I think that's about it. I'm going to dive into this sheet. Okay, yeah, so I was just saying, I think you guys have a day off next week on Wednesday, so there's no labs next week. Yeah, so that gives you some relief. It's like spring break, right? For the freshmen in the room, hopefully you'll get to experience a real spring break where you don't have to be on campus and stuff. But we don't have a day off. So we are a Tuesday, Thursday class. That means we'll have class on Tuesday, we'll have class on Thursday. There'll be real stuff. Oh, I know what I wanted to finish up with. The next exam will be May the 4th, okay? So it's like, I think that's, I'll have to double check the syllabus, but basically, May 1st? May 4th. Okay. It's the last class day before, it's the second to last class day before the final. All right, the final will be according to the university's schedule, which is Saturday morning, May 8th, 9 a.m. I will probably, if I can get a room, right now getting rooms is really hard. If I can get a room, I will try to offer an alternate time later in the week. But if I do offer that alternate time, those will be the only 2 times offered. If I don't offer an alternate time, May 8th is it, okay? All right, the final is cumulative. The other thing is on Thursday, I'm going to email you the final problem set. You should probably start that like now. Do a question every couple of days. I mean, it's long is what I'm saying. Okay, I wanted to start with a mechanism on this sheet. Come on. All right. And then the product all right, so I asked for how this happens. Some common things that people do wrong. One is several of you on the assignment got a different final product. All right, don't do that. I've told you what the final product is. On the mechanism question, I'm not asking you to predict anything. I'm not asking you to predict what the outcome is. That's the product. All right, so drawing a correct mechanism to a different product is not answering the question. So is there a base in the whole mixture, is there a base strong enough to pull off the OH proton? All right, so a lot of people did something like this. All right, in some step, right, there's a neutral OH alcohol. You've got water, you've got sodium bicarbonate. All right, so a lot of people wanted to get rid of this H. Obviously, you get rid of the H at some point, right? The H is not on this oxygen. So a lot of people are like, oh, I know how to get rid of that. I do an acid-base reaction. But you have to have a base strong enough to do it. All right? You can't just take that proton off because you think you need to. And if you look at this, H3O plus is a strong acid. You guys should know that. A localized O minus is going to be a strong base. Right? This is essentially like saying water makes H3O plus and hydroxide. And that's a reaction you guys have seen in Gen Chem, but the equilibrium favors by 7 or 8 orders of magnitude just being water. Okay, so don't do this. So the first thing that happens, the alkene is going to attack the iodonium. This is a reversible process. You get an iodonium ion. Quite a few people drew this as a carbocation, so they drew, the bond, the bond at the carbon at the end of the chain bonded to I, and a positive here. And that's okay. That's not great, but it's okay. I've used that structure to explain this as well. So now, from the iodonium, this is just a halohydrin. The thing that a lot of people didn't recognize, this is just a halohydrin reaction. The ROH is in the molecule. Okay, so now this oxygen is going to attack the more substituted carbon. That carbon iodide bond breaks, the electrons go to the I. So again, I'll let you write that down. So the curved arrow in the mechanism is going to start with electrons. It's going to start with this lone pair. It's going to go to a partial positive carbon, and it's going to go to the carbon in the halonium ion that would make the best positive charge. Right? So that thing right there is partial positive. So is that one, but a secondary carbon is going to be a better cation than a primary. And it does this with the H still attached. All right, so the product we get, and I can number these if you'd like. Oh, also, make sure you write your formal charges. A lot of people on that addition worksheet basically answer the questions correctly. Everything looks good, arrows are pushed the right way, structures are right. There's not a formal charge to be seen. All right, that's going to be a huge deduction. Formal charges have to be on the structure. So if we number these, all right, there's 5 carbons. There's 5 carbons in the product. The oxygen is bonded to 1, and it's going to end up being bonded to 4. All right, so oxygen makes a bond to C4. The C4 iodide bond breaks, I stays on 5. All right, now, and I know this probably seems really picky. This whole thing about don't take the proton off first. The proton comes off here at the end. So here at the end, that OH, that positively charged O with an H on it, that H now is really acidic. Right? It's a lot more acidic than a neutral OH. So now, sodium bicarbonate, water and sodium bicarbonate. Sodium bicarbonate you guys hopefully have played with at home. Maybe you baked a cake. Maybe you dumped vinegar into it. Maybe you just stuck it in the back of the refrigerator. But one way or the other, you've worked with this. It's a basic material. HCO3 minus. The structure for this is that. Again, from the arrow to the H, and then the OH bond to the O. So bicarbonate is a weak base. Water is a weak base. You could use water there. It would not be correct, but I'd be happier with it than taking the proton off first. So again, in the halohydrin reaction, the alcohol or the water is going to attack as a neutral. All right? hang on. It really, I mean, I understand why you would prefer, right? This just looks so much more enticing. Right? Have the O minus do that, and then you're done. So taking that proton off early seems like a good idea. Every time, and this, I would like you guys to think of this every time you pull a proton off. All right, so rest of this class, when we do chapter 7, when we come to 9, when we do 10 and 11, we're going to see a lot of reactions where protons get pulled off of molecules. Every time you do that, you got to ask yourself, right, all right, I need to get rid of this H. I know I need to get rid of this H. When does it happen? I pull a neutral OH alcohol proton off with water. You've got to ask yourself, does that look like an acid-base reaction that makes sense? That's why understanding chapter 3 is really important. All right? Chapter 3 is not self-contained to chapter 3. It's going to come up over and over again. Questions on this one? Yeah. I might use a name, but you won't need to know the name of a reaction to answer the question. The names of reactions facilitates communication, right? And that's all names are ever really useful for. They let us, like, that's why we all have, okay, I'm not going to get that. You guys have an exam and are stressed out. I won't go off on a tangent, but names are always only used to facilitate conversation. So rather than say, that reaction where you add Br2 and water and you get a bromine and an alcohol, you just say halohydrin and you're there. But you will not have to have that memorized to answer a question about it. Something else kind of similar. Memories shot. All right. Okay, so let's say you're going to protonate. Actually, go ahead and draw the product and the mechanism for that. Okay, so this is the first one we did, the addition of HX to an alkene. Markovnikov's rule, the X is going to go in the more substituted carbon. You're going to go through the more stable carbocation. So H is going here, Br is going there. How many chiral centers does that molecule have? Is it R or is it S? What was that? Yeah, so it's 50-50. Okay, so the intermediate, let's do the mechanism then. Okay, so the mechanism, again, every mechanistic arrow always starts with electrons. Something with electrons kicks these reactions off. In this case, it's the pi electrons, okay? They're going to the strong acid. So one way of thinking about this, these pi electrons, it's a neutral molecule. You could put this molecule in a bottle, put it on your shelf, come back 60 years from now. If the building's still here, that bottle is there with that compound. H can't have two bonds. So again, the pi bond, the pi electrons attack the H. And then the second arrow also starts with electrons. It goes from the bonding electrons to the Br. And this is going to give us the tertiary carbocation. The H of the HBr adds on that secondary carbon. And now Br minus is left. And so now we have this trigonal planar cation. It's flat. The Br minus can come from the top. It can come from the bottom. So it's not R or S. It's both, right? If it comes from the, let's see. So the methyl would be the low priority group. If the methyl's back, Br. So if the Br is in front, that's an S chiral center. So if the Br attacks from the front, you get S. If the Br attacks from the back, you'd get R. There's no reason here to prefer one side or the other. Now, you could have a situation where, right? So it's flat here. I'm making things up now, right? If you had that chiral center, now that molecule itself is chiral. So you can have a chiral molecule that has one enantiomer favor, like, so the molecule I just drew, that weird molecule on the second board, right? It has two chiral centers, and I've shown them with the absolute configuration they have. So now, right, the Br attacking from here, or the Br coming from behind, you got two really bulky groups sitting in front of the front, poking out here, right? So it's going to be easier for the Br to come from the back. Does that make sense? Yeah.
The initial H proton,
Yeah.
how come it goes right there and not like off of the carbocation?
What? It's simply, yeah, because it could, if it goes here, you get a tertiary carbocation.
Yeah.
If it goes there, you get a secondary carbocation.
Okay.
Right? So you're going to get the more stable carbocation. And the other way to think about that, and this gets to a mechanistic quirk I want to tell you to avoid, you can almost think about like, almost think about a resonance structure of the double bond. Take the pi electrons and put them on one carbon or the other. The one that's got the two electrons on the secondary carbon is more stable than having it on the tertiary carbon because of the cation you get. All right, so as these two are sharing electrons, really the secondary carbon's taking more of the electrons than the tertiary. So it's a more basic. That's a way to think about it. It's a fine way to think about it. I see a lot of people that draw the mechanism. I'm going to redraw it down here. And I mean, I see this every year. It's a understandable thing to do. But I want to tell you not to do it. So I see this, sort of showing the pi electrons moving to one carbon and then that carbon attacking. All right, you never want to have two arrows doing that, right? It's the pi electrons just attack. So you want just one arrow here from the electrons to the H, not an arrow showing electrons going to the carbon. I guess that'd be the wrong one anyway, wouldn't it? Here, I can fix that. Right, you don't want the pi electrons doing just going to an atom and then the atom attacking. Yep. So, well, yeah, so if these were racemic, you'd still get a racemic here. So, So if you have a reaction where you have either achiral reagents, so if everything in the mixture is achiral, or if you have a reaction where you have a chiral reagent but it's racemic, then the products have to be racemic. All right? There has to be some reason, right? So if a nucleophile is going to attack this carbocation, there has to be some reason for it to come in only from one direction. Right? If we're trying to say you're going to end up with a non-racemic mixture, there has to be some reason for the nucleophile to come in from one direction or the other. Remember, these are physical things. We can't see them, I think. So one of the things that kind of plagues all of us thinking about this, but certainly new students, is you can't see these objects. So it's kind of just a thought experiment. The word racemic's in your head. I got to memorize that it's racemic. And like I would advise that. Pretty much every reaction in Chapter 8 probably going to give you racemic products. So what does that mean? If you think about it physically, to get a non-racemic product, that means this new bond that makes the chiral center, the new thing coming in has to come from one side or the other preferentially. If there's not a physical reason for it to come in from one side rather than the other, it won't. Okay, so on this blue cation, there's the front and the back are equally the same. On the one I've drawn down here, like it's contrived, but I've put chiral centers on either side of the carbocation, and I've put them both in front. All right, so now in that conformation, clearly the nucleophile wants to come from the back. All right, so you have to have something. That's what I mean. So if you have if this molecule were racemic, you'd get racemic. And actually, the other thing is, this doesn't go to enantiomers. This goes to you're looking at diastereoselectivity. selectivity. Right? So the two underlined chiral centers aren't going to change. If the nucleophile comes from the front, you get the diastereomer of what you get if the nucleophile comes from the back. Diastereomers have different stabilities. You guys will remember that from Chapter 4 where we looked at cyclohexanes. So you can make a reaction could give a non-50-50 ratio of diastereomers. It can't give non-50-50 enantiomers unless there's some single enantiomer influence in there. Yeah.
Would you want us to show the hydrogen bond in that?
No. I drew it in because a lot of people are drawing their H's in to make sure they see it. You don't have to draw that H. If it helps you to see the H, if it helps you to understand the reaction to draw that H, draw the H. If it doesn't, don't. I was going to put one last thing down here on this sort of general thing. And we'll talk more about this probably toward the end of the class, like the end of the course. If you have in your, either in the starting material or the reagents or the reactants or a catalyst, it's got to be something in the reagent group. If it's chiral and non-racemic, then you can get non-racemic products. And that's the only way, all right? Something in the reaction has to be non-racemic to end up with a non-racemic product. It seemed like there were a couple of other things. Oh, yeah. Yes. And I'll do one more thing, and then I'll take some questions. Draw the product. Include all relevant stereochemistry. Okay, so you don't have to know the mechanism of this reaction. So this is hydrogenation of an alkene. Alkynes, triple bonds can also be. I should have put that in there. Carbon-carbon triple bond also gets hydrogenated. I know you guys didn't do it, but I'll put this in here as well. Product's going to be the same, actually. All right, I changed that double bond to a triple bond. So H2 and a transition metal will break the pi bond, break every pi bond in an alkene or an alkyne, and add an H to both carbons, right? If I break the pi bond, each carbon is going to be down a bond. You replace that bond with an H. So, hydrogen, 5 atmospheres. That's a pressure. So the way to measure the concentration of a gas is by pressure. Right? 5 atmospheres of hydrogen is a lot of hydrogen. So you don't have one molecule of hydrogen. A lot of folks on the addition worksheet just reduced one double bond, just hydrogenated one double bond. Right? Every alkene and alkyne is going to hydrogenate in this reaction, with the exception of the benzene ones. And this one, I think I did this in class the other day, but I don't blame you guys a bit for being a little skeptical of this. So this double bond hydrogenates. Nothing happens to this chiral center, all right? So this chiral center is still up. This triple bond hydrogenates. We have 1, 2, 3 carbons here. 1, 2, 3. Our benzene stays intact. I will come back and talk about this in a minute. Good, I saw a couple of people get pissed off there. That benzene stays intact. This double bond gets 2 hydrogens there. They're both achiral. We're going to make a chiral center here. And then we'll reduce that double bond. So 1, 2, 3. All right, so first on the chiral centers, this chiral center is not doing any chemistry, right? Hydrogen doesn't do anything to sp3 carbons. So that one stays out. We make a chiral center here. Now again, that alkene, the carbons are sp2 hybridized, they're trigonal planar. So the hydrogen can come from the top, the hydrogen can come from the back. And we'd get diastereomers, right? But the only chiral thing in the molecule is way, way away from that. Like there's really no difference in energy coming front or back here. Okay, so we'd get both. Roughly, this is going to be a 50-50 mix of R and S. All right, this is no longer plus an enantiomer, right? If it's S here, it's S plus this absolute configuration, R plus that one. You'd get diastereomers, so you'd get 2 different diastereomers in this molecule. All right, every alkene and alkyne gets reduced. Now, you'll recognize benzene from the aromatic region on an NMR. It's a 6-membered ring with 3 double bonds. Every carbon is sp2. They're all trigonal planar. Right? What's the bond angle of an sp2 carbon? (120). What's the interior angle of a regular hexagon? Take a stab at it. Huh? It's 120. So a regular hexagon and an sp2 trigonal planar carbon line up exactly. That's not really why it's that stable, but it helps. And then remember, you've got delocalization here. I've told a bunch of you individually, I think I mentioned it in the last class, this probably should go in early in Orgo 1. Benzenes are benzenes. They have a quantum mechanical stability that is outside the scope of this class, but they're way more, they're already, you got 3 conjugated double bonds, you've got delocalized electrons, you've got like no angle strain, right, no ring strain. The geometry of the ring fits the geometry of the hybridization of the carbons. So already from Lewis structure, you'd say that's pretty stable. But then it's got this added quantum mechanical stability. And what that means is that benzenes are not alkenes, even though they rhyme. Right? Benzenes are not going to do any of the chapter 8 reactions. Totally fair if, you know, like on the addition homework, maybe 10%, maybe 20% of you all like did alkene reactions with benzenes. I totally get why that is, and I wish I had time to explain it better, but I've got to basically just tell you that benzenes don't do that, okay? So that's hydrogenation. You really can't kind of, like we can add one equivalent of a liquid or one equivalent of a solid. You can weigh it out. You can measure the volume. You can't really add one equivalent of hydrogen gas. Right? So you just, what we do is we just flood it and hydrogenate everything. Questions about hydrogenation? All right. So no mechanism on the exam for this. Let's see, off the top of my head, no mechanism for this or any of the anti-Markovnikov reactions. Or the epoxidation. So, oh, that's one more I'm going to come back to. Or there might be another one. Is there another one? What's that? Okay, good. I think I was thinking hydrogenation. All right, like I said, one last thing, and then I'll take questions. I only meant to go 30 minutes. Couple of people on the exam did this, and I've seen this in the past. All right, draw me the product of that reaction. All right, product of that with MCPBA, and again, this is one you just basically memorized. You don't have to know this mechanism. MCPBA just makes an epoxide. So it takes a double bond, breaks the pi bond, puts an O shared between the two. Looks a lot like the halonium ion, but it's stable because that O is neutral. A lot of folks on the worksheet then drew that. And basically what they were saying, they actually wrote in here like water and H3O+. All right? The reason I'm bringing this up, so if this were true, if we took the epoxide and we treated that with water, aqueous acid, then you would get the transdiol. Here's my warning to you. Do not add reagents to what I give. Like if you're convinced that I haven't put all the reagents there, ask me. Like, didn't you mean to write this other thing in there? 98% of the time, the answer is going to be no. I told you exactly what I want. All right? You can't just invent reagents. Believe me, I've done this as well, right? Like, well, I don't know the answer to that question, so here you go, professor. I'll answer this question. Turns out professors have seen that and done that. Okay, so don't add reagents to anything. If you don't think all the reagents are there, ask me. This is true for predicting a product. It's also true for mechanisms. So a lot of times I'll give a mechanism problem and people will be like, oh, well then water comes in. There's not always water there. There's not always whatever reagent you would like. Like I said, if you think it should be, maybe I made a typo, say something, but don't just assume it's there. Yep.
For the epoxide, why aren't they like cis?
So, excellent segue. So the mechanism of the MCPBA step is not covered. This mechanism is covered. All right, and again, it's just like the halonium reaction. It really, if you guys know the halohydrin reaction, this is the same mechanism. But first you have to protonate the oxygen. All right, so it's racemic, right? The epoxide is racemic. That oxygen can come from the top or the back, either way. Now, once you protonate the oxygen with a strong acid, now this is a lot more reactive. Water is going to do a backside attack on the more substituted carbon, break the CO bond. So that backside attack, again, it comes from opposite the oxygen that's going to be leaving that carbon. And when that happens, that inverts the stereochemistry there. So this would come forward. The OH, all right. Let me draw and then I'll talk. All right, so water comes in as water, not as hydroxide. If you guys are focused on this, you're like, I need to add an OH. And again, this goes back to the thing about acid-base chemistry I was talking about. You want to add an OH, it is almost instinctive to say hydroxide. Okay? But it doesn't. We're under acidic conditions, okay? So you've got a lot of acid, you don't have much water. So water comes in as water, and then another water, again, you've got lots of water here, right? Another water takes that proton and gives us the diol. Yeah.
So for the epoxide, you would put two dashes next to the O and then a wedge next to the carbon group?
Yeah, I mean, well, so this is racemic. But the thing is, you've got the OHs are trans to one another. All right? So anti-addition means that they come from opposite sides. If neither of those carbons is chiral, you can't tell. But if you have a ring or they're chiral centers, you can. And so you've got to show the stereochemistry for all this. And this is racemic. All right? By not showing any stereochemistry there, I'm showing it being racemic. If you have a chiral center and you don't show, like you just draw them as lines, you're saying it's racemic. All right, and the other thing is, this O can't be trans to itself, right? I don't have to show cis and trans there because it's one atom, right? That O is either in front of the board or it's behind the board. The O can't be in front of one carbon and behind the other carbon. Oh, the last thing, just like tip. I showed this to a bunch of folks in office hours yesterday. This seems to be a point of confusion for a lot of folks at this point. OH does not always mean hydroxide, right? If I say ETOH, that's ethanol. You've got a covalent carbon-oxygen bond. You do not have hydroxide in ethanol, right? If ethanol was ethyl plus and hydroxide, Thursday nights would be a lot worse. All right? You can't drink hydroxide. That's a good rule of thumb. So if you see an OH paired with something carbon, methyl, ethyl, hexadecyl, whatever, that is a covalent bond. That's a neutral OH. It's more like water. It's a neutral OH. It's a weak base. It's a weak acid. If you see OH paired with a metal, I've done lithium here, but it could be sodium, potassium, cesium, any of the metals really, anything there in yellow or even green, and then orange. Any of those, the OH is hydroxide, OH minus. It's a strong base. It's a good nucleophile. Right? Fundamentally a different thing. All right, I really told myself I'd shut up after 30 minutes, so I'll take questions now. Could be on this, could be on anything else pertaining to exam 2.
I have a question for the, you just slide the board down, going back to the BR. Draw another arrow then with BR.
On the mechanism?
Yeah.
Yeah, absolutely, right? Sorry, I didn't finish this. So now the second arrow, there's only one arrow at that point, from the BR minus to the plus. The other thing I guess I should make a point of, anytime you draw one of these arrows are either going to make or break bonds. Every curved arrow will make or break a bond. Right? So the Br minus arrow to the C plus, that's making a bromine-carbon bond. The arrow from the pi bond to the H is making a carbon-hydrogen bond. The arrow from the HBr shared electrons to the Br breaks a bond. So the mechanism, if you speak curved arrow mechanisms, every curved arrow will tell you what bonds break, what bonds are made. And that's all that happens, okay? So in a mechanism, right, the Br attacks the C plus, that makes a carbon-bromide bond. Nothing happens anywhere else in the molecule. So you can't drop atoms, you can't rearrange atoms. The only thing that changes there is the bromine winds up bonded to the carbon. So if you see if I give you a mechanism, like here's a molecule with a bunch of curved arrows on it, you should be able to interpret from that what bonds are made, what bonds are broken. Don't do anything to any atoms that don't have an arrow somewhere near it. Yeah. So okay, this is more business. It's more of a business question than a chemistry question, but it's an important one. Looking at the addition worksheet, the first page, this page, right? I ask what the product is. Right, okay, good. I don't always read my assignments that carefully. So I'm asking what the product is. What I'm going to grade, if I do that and I shouldn't say if, on that type of question on the exam, I'm going to ask you to draw a product. I'm going to look at what you draw as the product. If you want to draw the mechanism because it helps you, that's great. Certainly if you do that and you get it wrong and I can see what your thought process was, maybe I can help. But all I'm grading is the product. So if you draw if you draw an incorrect mechanism and the right product, congratulations, you got the thing right. If you draw the right mechanism and the wrong product, that's life, man. So you can do everything absolutely correctly and still lose. So yeah, but business-wise, on a question where I say draw the mechanism, then I'm grading the whole mechanism. And I had this conversation with another student in office hours today, that on this test especially, right, there's a mechanism sheet floating around out there where I basically give you elementary steps. It's like if I had given you here, here, and here, and said supply the arrows, right? So you don't have to come up with the entire mechanism yourself. You just have to connect each one with arrows. I can ask either of those kind of questions. I could just give you like the one on the on the chapter 8 set, right? Here's an overall reaction, draw the entire mechanism. Frankly, at this point, a lot of that is memorization for you guys, right? Like coming up with that entire mechanism would be a lot just from scratch. The questions on the mechanism sheet, either where I give you all the intermediates or where I give you a structure and I draw the curved arrows and I ask you what the product is. Like you'll probably see both of those on this test, honestly. There was another, yeah.
How do you know what reactions to master?
We'll do that in just a second. Was that, were you on this other? No. So any of these, honestly, I probably won't even look at that. So I got caught up, Juliet, I will come back to what's faster. I kind of, at this point, I don't really care. Like I've made my this is actually this is really an important like chemical concept. Even if you don't end up becoming any kind of a chemist, if you work tangentially with the chemical field, you should know that. But on this exam, if I get like on this page, right, so the top molecule here, there's a chiral center, it's a racemic mixture. If you don't show the chirality, like if you just show a line to OH, or if you draw either enantiomer, I'm probably fine. However, what I will tell you is, as you may have guessed, like there's 6 or 7 or 8 people that teach organic chemistry at Wake Forest. I can definitively tell you right now, you will not have me for Orgo 2. I guess I can't do that. You won't have me for Orgo 2 next fall. So if you wait down the road, maybe I'll catch up to you. If you don't take it next fall, maybe I'll teach it at some point. Anyway, there are definitely, I have colleagues who if you don't put plus enantiomer, and in Orgo 2, you start to have a better handle on things. It's not all new. Like, it gets easier. But if you don't recognize, that this reaction would give one enantiomer over the other, or this reaction will give racemic products, they'll pound you. All right? So we all sort of have our little thing, our pet peeves, right? Like formal charges bug me. People that don't draw formal charges. One I try to correct early. This was a product on one of the problems. That probably looks fine to you guys, right? That really bugs me. I may have noted it on your edition. Right now, on exam 2, probably I won't say anything, but by the final I will. This carbon is not bonded to the ethyl group. This carbon is bonded to an oxygen. So don't do that. Do that. And like I said, I've got colleagues that would not care. So I was told, somebody told me, somebody had an Orgo 1, did well, did fine in Orgo 2 too, Orgo 2 as well, but lost a bunch of points on that. So I try to make sure now that you know that. Like I said, we're going to come back before the end of the class and talk about reactions that give a non-racemic mixture of enantiomers. It's a really important category. All right, so this question about how do you tell the fastest reaction. Let's do one of those. So rank these one. Tell me which one's fastest. Tell me which one's slowest. Also, as you're thinking about that, the addition of HX is a two-step reaction. All right, we're definitely going to talk about kinetics and rates more in the next module. But as you look at this, we got two steps here. So we've got HBr adding over here. Two steps, right? One step is going to be faster than the other usually. Better way to say that. One step's going to be slower than the other. The slow step determines the reaction, or the rate of the reaction. So this first step is slow. Second step is relatively fast. All right, those are comparative terms. So the first step is two neutral molecules, right, reacting to give a carbocation, a molecule that doesn't have a full octet. That was something else in the resonance structures. I'm not going to go into a lot of detail on it, but ranking resonance structures, like is a carbon positive better or worse than a nitrogen positive? By electronegativity, you'd want the carbon positive. But in the question I'm talking about on the review assignment or the addition assignment, the one with the N positive has all the atoms with a full octet. Having all the atoms with a full octet is really important. All right, here we go from all the atoms having a full octet to an atom that doesn't have a full octet. That's way uphill in energy, and it's slow. Conversely, the second step, we have an anion reacting with a cation. We have a molecule without a full octet getting electrons. That's going to be pretty fast. So what determines the overall rate is this step. And there's two ways of thinking about this. So the actual question, right, was not, you probably didn't want me to put up a problem. You wanted me to answer your question. So what you need to figure out is two ways of thinking about this. Which cation is more stable? And that probably forms fastest. And when I say probably, you should bet that way today. Or which alkene is more electron rich? And these are the same question, all right? I'm saying you can ask these two different questions. They're the same question. You want to look at what is bonded to the alkene and think about how it will stabilize the intermediate cation and how it affects the electron density of the alkene. So if we look at these cation intermediates, so in blue there's the cation we get from protonating the top molecule, the middle. All right, so there are our three cations. which of those cations is most stable? Think about resonance. So we got the middle because there's resonance there, but I'm going to draw the resonance structure here in a minute. So, well, actually, I'll just go ahead and do it. Again, carbon doesn't have a full octet here. So we can draw a resonance structure, but that leaves us with an oxygen that's positive, and not just an oxygen that's positive, but an oxygen that doesn't have a full octet. All right, so you guys have seen plenty of O positives. H3O plus, I've drawn you protonated carbonyls, but those oxygens always have 8 electrons. And so an oxygen without a full octet is quite unstable. And if you think about resonance, the carbonyl carbon, that carbon has a strong partial positive charge, and it's sitting next to a positive carbon. All right, that's destabilizing. So you can't, a real shorthand, and I totally get why you guys would think at this point, there's a resonance structure there, that should stabilize it. We tell you that the more resonance structures you can draw, the better. All right? That's not always the case. If one of the resonance structures is particularly bad, meaning unstable, probably won't form. On the other hand, on the top, we can take this nitrogen, the lone pair on the nitrogen, and now we get a molecule, still a positive charge, but all the atoms have a full octet. All right, keep that in mind. The octet rule is a rule for a reason. Atoms, the second row elements, want to have a full octet before pretty much any other consideration. And so this winds up, the middle one winds up being the slow reaction, the top winds up being the fast. And then that secondary cation, the localized secondary cation at the bottom is kind of in between. Now, I answered the question using which cation is more stable. You can also think about it in terms of how electron-rich the alkene is. So we can think about it draw resonance structures of the starting material. Right, so this red structure I just drew has a negative charge. The nitrogen's pushing electrons into the alkene. Right? The carbon that's going to eventually grab the H in one resonance structure has a negative charge. And that's going to make it more basic. A negative carbon is going to be more basic than a neutral carbon. On the other hand, on the middle one, the carbonyl is actually pulling the electrons out. This oxygen is pulling the electrons out of the alkene. And in that resonance structure, the carbon that's going to grab the H has actually got a positive charge. All right? So in the middle case, the substituent on the alkene, the carbonyl, is pulling electrons away from the alkene. In the top case, the nitrogen is pushing electrons into the alkene. Right? If you think about this reaction, right, there's the mechanism. Right? The alkene is pushing, the electrons are going from the alkene to the H. So what you would like the R in the resonance structure to be pushing electrons in. Right, so any R group there that pushes electrons toward the alkene will speed the reaction up. Any R that's pulling electrons out of the alkene is going to slow it down. Now, that second bit is a more sophisticated way to think about it, and one that, admittedly, I didn't do in class before giving you that assignment. You can think about it, whatever the effect of R is, does it push electrons in or pull electrons out? It's doing it to the cation as well. Right? So if you think about the intermediate cation that forms in the slow step, if there's something bonded to the carbon with the cation that's pushing electrons toward it, that's going to stabilize it. If there's something bonded to a positive charge that's pulling electrons out, that's going to destabilize it. Right? So these two questions are the same. Think about it, whichever way makes the most sense to you. Look at the cation or look at the initial alkene, either way. That help? Okay. Yeah.
Wouldn't the nitrogen be more electronegative than the carbon, so it would like draw electrons away in the top one?
Someday I'm going to try to convince general chemistry teachers not to teach electronegativity. It's fundamental, but it's BS. Like so much of life. Anyway, yes, nitrogen is more electronegative than carbon. The electronegative thing in this one, though, is not the carbon, but the oxygen. Right? The carbonyl is pulling electron density toward it. And then this gets to, when we get to this semester. We may not talk about it this semester, but definitely in Orgo 2 you see this. There are resonance effects and inductive effects. Right? ARIO, R and I. And R and I can compete with one another. So the nitrogen, yes, the nitrogen is electronegative. By induction, it's pulling, through the sigma bond, it's pulling electrons toward it, right? If I ask you guys to, what's the polarity of this bond? Obviously, the nitrogen's partial negative, the carbon's partial positive. And that is true. It's actually true of this molecule, the one I just drew it on as well. But the lone pair on nitrogen, by resonance, donates. So nitrogen and oxygen are resonance donators, inductive withdrawers. And so now you're down to which is the more dominant effect. And this is where it gets a little dicey. If the atoms are in the same same period, right? So they're both second row elements or third row elements. Like that means their orbitals overlap really well. So the lone pair on the nitrogen overlaps with this p orbital really well. And so resonance is more important than induction. If the nitrogen were a chlorine, right? Chlorine is a bigger atom. The orbitals don't overlap as well. Induction is more important. You can draw exactly the same resonance structure, but chlorine destabilizes a cation rather than stabilizes it. Focus on resonance right now. More.
So is the bonding reaction slower or faster than the middle one?
Faster. That cation is really bad. Right? So I know a lot of people looked at that and were like, resonance, it's got to be stable. And yeah, and it makes sense given what you've seen. Basically, oxygen without a full octet doesn't form. Obviously, like everything I tell you in here, there's going to be exceptions. There are molecules. I could go upstairs right now and make you a molecule that, actually, you guys, who has lab today? Raise your hand if you're in my lab today. You guys will make an oxygen that doesn't have a full octet. So 23 minutes before I make you do it, I tell you it can't happen. The benzoyl peroxide in today's lab, this is a palate cleanser maybe. So the rest of you have either done this. Oh, by the way, pH is a benzene. Stands for phenyl. Long linguistic story there. So this is benzoyl peroxide. You see benzoyl peroxide in a lot of commonly used products, especially in skincare. You see peroxides in a lot of products, period. All right, the peroxide bond is really useful, by which I mean it's explosive. Okay, so the oxygen-oxygen bond is extremely weak. There's, again, a long story there. So in the lab, like I said, I'm going to show this. I'm going to undo hours of work. In the lab, when you heat this up, the OO bond undergoes homolytic cleavage. I've just drawn the curved arrows for that. In a radical mechanism, you can have arrows go different ways. You can have arrows come together. And the other thing, I don't know if you're in the front row, you definitely see this. I've drawn each of these arrows with a single barb. All right? In our mechanisms that I draw up here, there's 2 barbs, and probably up to now you've just thought, well, yeah, of course you drew 2 barbs because that's how you draw arrows. The 2 barbs each represent an electron. Okay? The curved arrow is a pair of electrons. Each barb is an electron. So in a radical reaction where you have single electrons reacting, 1 barb. I'm not going to ask you guys to draw a radical mechanism in this class, but your lab instructor might, I don't know. So the OO bond undergoes homolytic cleavage really easily. And that is good to, so then that initiates reactions we're going to get out of this. All right, there's a lone pair there. You get an oxygen that is electrically neutral, but it only has 7 electrons. And that is why it is so reactive. Okay? So it's going to initiate this polymerization that's going to give you plexiglass. In skincare, right, your body heat homolyzes the OO bond. You get these radicals on your skin. Radicals are really damaging. Okay? So if there's any bacteria floating around, you can pull electrons out of their DNA. You can do all sorts of stuff. Same thing with H2O2, hydrogen peroxide that you put on scabs and stuff, like a wound. It goes in and sterilizes. And like I said, if you dip, I don't know if you could actually do this or not. I'm not BSing, but like H2O2 is toxic. So pour a little on it also doesn't go through your skin, so you can pour it on your skin, clean off your skin. You know, if you drink it or swim in it, it would be bad. Yes, thank you.
The speed of reaction, is that have anything to do with secondary and tertiary and primary?
Sure, right. So I think the one on the review assignment was right 8 something here, and so the easiest way to think about that is the top reaction makes a tertiary cation. That's going to be easier than making a secondary cation. The stabilities of the 2 double bonds isn't quite exactly the same. The top alkene's actually a little more stable than the bottom alkene, right? And generally something that's more stable, you would think, well, that will react slower. But the difference in stability between the 2 alkenes is dwarfed by the difference in stability by the cations, right? The tertiary cation is way more stable than the secondary cation, so it forms fastest. The other way to think about this is an alkyl group is actually a weak electron donating group with that hyperconjugation I talked about. So one alkene has 2 electron donating groups on it. One only has 1. The one with 2 will be more, we say the alkene's more electron rich. So it's a better base or a nucleophile. All right, so I've robbed many minutes of you so far this semester by going over, so I'll stop 2 minutes shy. We're even. I know nobody feels even with me right now. So again, I'm in here tonight at 6:30. I do not have office hours before 6:30 because I'm teaching lab. And between lab and 6:30, I'm going to get dinner. So if you have questions, come tonight. If you don't, and if you can't come tonight and you have questions, I have some office hours tomorrow. All right, that's it. I'll see you.